Hello, everyone, and welcome to the second keynote of HPG 2022. My name is Tammy Boubeker from Adobe Research, and it's my pleasure to welcome for this second keynote Shoaib Kamil, who's a principal research scientist who leads the Programming Language and Performance Group in the Computational Creativity Lab at Adobe Research. His main areas of focus include compilers, computer-assisted programming, and high-performance computing. Prior to joining Adobe, he worked at MIT and at the Lawrence Berkeley National Laboratory and obtained his PhD in computer science from Berkeley. The talk today is entitled Toward Computer-Assisted High Performance for Graphics. Shoaib, up to you.
Thank you, Tammy. First, I'd like to thank the committee and everybody for inviting me for this talk. It is always somewhat of a strange experience to give a talk in a virtual environment, particularly because I can see nobody's reactions. So hopefully people will have great questions at the end of the session. So thank you. I wanted to start by first adding a towards to the title of my talk, because I think a lot of what I'm going to talk about is initial research that we've done in different areas of computer-assisted high performance and some open challenges when it comes to graphics. So to begin with, I'm sure you have all seen this or similar charts. If we look at hardware performance improvements for CPUs in the past 50 years, we can see that the single-threaded performance, which is in blue, has been increasing, but has started to level off. And instead, what hardware manufacturers have begun doing is increasing the number of logical cores. So really, the performance that you can obtain is the multiplication of these two, which is maybe better charted on a chart like this, which is from Liserson. And so here we're just looking at spec int, which is, admittedly a really artificial benchmark, and the performance thereof. And if you kind of follow the curve here, you can see that we, for the most part, have been able to continue scaling hardware performance by taking advantage of multi-threaded CPUs. Similarly, if you look at performance of GPUs, these have continued to increase steadily in the past years. However, I think all of us can attest to writing high-performance software is not necessarily gaining the same kinds of improvements. So we're basically trying to write high-performance software with primitive tools. And that's not to dismiss the huge advantages of languages like CUDA, which have made it possible to take advantage of GPUs for general programming. But it is the case that we're making hardware much faster and much more powerful. But for the most part, the driver of this increased use of compute is really machine learning. So I am going to mostly not talk about machine learning in this talk. I think there's many more qualified people who can say a lot more about that. But one of the successes for machine learning really is leveraging the massive amounts of compute that are available today. The rest of us, we've had some advantages, like I said, from things like CUDA. We also have better static analysis tools, which kind of run in the background. If you use Xcode or Visual Studio Code, you get some semantic highlighting now, which is indeed a big improvement over the previous state of having to just continually run the compiler to tell you the error messages. But for the most part, I would argue that we don't really have the same advantages. As hardware has increased its performance, writing software for that hardware has not gotten much easier. So a big thrust of the research that I work on and my group at Adobe works on is computer-aided programming. And our goal here is to harness the power of hardware in order to make it easier to write high-performance code. And today I'm going to kind of talk about that in terms of a toolbox of techniques. I'm going to talk about scheduling languages, program synthesis, and sparsity-specific specialization as three manifestations of the way we can use increased hardware compute ability to make programming more efficient and more productive. So let's start with scheduling languages. Um, The key here is that manually writing fast code is truly tedious. So if you have something like a 3x3 box filter, which is probably code you've seen uh, dozens of times if you've done any image processing, writing the straightforward code is fairly easy, but turning it into fast code requires manually applying multiple different optimizations, each of which interact with one another in non-trivial ways. So this is just a 3x3 box blur. You take this image of a parrot and you blur it. Really simple algorithm. But to actually make this run fast, you have to transform this into this relatively gobbledygook amount of code, which applies tiling, vectorization, stores intermediates more efficiently by tile rather than computing an entire intermediate image. And all of the math, all of the loop bounds, all of the transformations here are incredibly tedious for programmers to write. So I'm sure most, if not all of you, have heard about Halide, the language for dense computations that was initially published in 2012. This is work by Jonathan Reagan Kelly and Andrew Adams and a bunch of others. But basically, the idea here is that you define the computation without really thinking about or defining how that computation occurs. And then separately, you schedule the computation using a second scheduling language. And in this language, you specify how the intermediate data are stored, the order of computation, whether you compute on CPUs with vectorization and in parallel, or whether you compute on GPUs, or whether you use a combination of those, whether you store things in shared memory, what is the tile size for your GPU loops, and so on. The key idea here is that separating out these two allows one to explore different optimizations without needing to rewrite the algorithm. So in the previous example, each time I applied a optimization, I would essentially have to rewrite the entire loop nest. The key idea with scheduling languages is that the programmer can simply change a few lines that specify how the computation occurs, and the compiler takes care of mapping that to the actual hardware based on the constructs that the programmer specified. So what this really enables is that the compiler only needs to ensure that the transformation is valid, not whether it will pay off. In traditional compilers, what we really have is a large set of mostly handwritten um, heuristics that decide whether a particular transformation will pay off. And these heuristics perform poorly when you need to apply a combination of transformations. So applying transformation A in isolation might not be profitable, and transformation B in isolation may not be profitable. But applying the combination of those can be. So really what scheduling languages are doing here is removing the need for the compiler to decide whether a particular optimization will pay off or not, and instead it orthogonalizes these concerns. That allows humans to concentrate on exploring optimizations once they've gotten their algorithm correct. Instead of rewriting the code over and over, they can quickly try, executing on a GPU, applying vectorization, deciding to do it to compute intermediates and tiles and so on. The other thing that this enables is that it allows us to, by orthogonalizing the problem, it allows us to assist programmers by building auto schedulers. And there's a rich set of papers in this area including a couple papers from Andrew Adams and a couple collaborators. This is from Mullapudi. What this chart is really showing here is the time it takes for two expert programmers to actually explore a large set of optimizations and to see how that pays off in terms of the throughput of the code that they created. So if you look at the time scale on the x-axis here, what you're seeing here is minutes. And I would argue for these kinds of algorithms, if one were to write this by hand, these would be, the x-axis here would have to be days, or at the very least hours, rather than minutes. But very quickly, an expert programmer like Andrew Adams here or Dylan Charlotte, they can quickly explore a large space and increase performance by orders of magnitude. Now, when it comes particularly for simulation, which is a big area of interest in graphics, I think we've had numerous attempts for various different kinds of simulation. Every year there's one or two languages that get published in venues like TOG or SIGGRAPH or HPG, and these all are fairly interesting, but none of them can really support the cross product of the simulation algorithm, the data structure, and the scheduling options based on that data structure and simulation algorithm. So in this sense, in one sense, one could say that we're still kind of exploring what is the halide of simulation. And part of that is simply because there's a huge diversity of simulation algorithm, there's a huge diversity of data structure, and given those, you end up with a massive scheduling space. Towards that, the tensor algebra compiler, or TACO, really tries to think about the low-level operations that are common across many of these simulation algorithms. So this really takes care of sparse and dense tensor algebra. However, it does not support some of the fundamental building blocks, such as direct solves or optimization, which continue to be open problems in scheduling languages. So for this particular tool, I think we have a lot of great evidence that we can orthogonalize the problem and make it easier for programmers to efficiently write high performance code, but we still don't have some kind of holy grail that works across um, multiple domains where data is not necessarily just operations on dense tensors. The second tool that I want to talk about here is called program synthesis. And program synthesis, I'm going to motivate by looking at the problem of legacy optimized code. So one of the problems that having manually optimized code introduces is that if you look at this code, it's not immediately obvious what the code actually does. And large, long-lived applications, such as those created by Adobe, do suffer from bit rot. We have a large legacy of optimizing code, and in many cases, the original authors that optimize that code are no longer available. The hardware has moved on. And even in some cases, the original authors of the algorithms may not even remember why they applied a particular optimization. So in order to take advantage of the scheduling language that I showed before, we really want to rewrite this code into domain-specific languages, or we want to at least, get the optimized code down to its most basic set of loops so that the algorithm is understandable, and we can try to understand how to optimize for modern hardware like GPUs and vectorized multi-threaded CPUs. So, I mean, if you didn't know what this piece of code that I showed earlier did, I think it would be quite confusing and difficult to, at a glance, try to understand what this code is trying to do. You have a bunch of intrinsics. Um, you have a lot of math computing sizes of tiles. Luckily, in this case, we have a few comments, but often legacy code does not contain any comments, and you just have a large set of spaghetti that you're trying to unravel to try to understand what a particular piece of code does and whether it can be computed more efficiently. So for that, we worked on this tool called Dexter, which the key idea here in Dexter is that we want to be able to take this highly optimized code, run it through a program that automatically deciphers what is this code in its most simple declarative form. And because our domain is image processing, we of course chose Halide as the output language because it makes it quite easy to see this, to see the semantics of the underlying code when you have it written out in this declarative fashion. And then we can do things like manually schedule that code for new hardware or throw the auto scheduling machinery at it so that um, we can, automatically come up with faster schedules and faster ways to perform that computation. So Dexter primarily works using this search process that consists of three parts. You have a search space that is defined by a grammar. So this is really a syntactic search space. This is things like, you know, our grammar, contains things like plus and multiply and, variables and memory accesses and so on. And then we have a search algorithm, and the combination of those two generates a proposed program that then gets passed to an equivalence checker that tries to check whether the proposed program is semantically equivalent to the original program. That is, for all possible inputs, are the outputs the same? So conceptually, this is quite a simple thing, but how do we actually check equivalence and how do we guide the search? Um, the search space, if you think about image processing, the search space really consists of any possible image processing program one could write. So that is far too large. Um, Starting with the equivalence check piece, the program synthesizer checks equivalence by encoding the semantics of the proposed solution. Uh, and then we pass that to a SMT solver, which is basically like a SAT solver with lots of machinery above it that kind of understands things that are not just um, Boolean expressions. And this SMT solver checks whether the semantics are equivalent using a very uh, difficult algorithm, let's say. I'll talk a bit more about that later. And it either returns back yes for all inputs. So these are equivalent. That is, the proposed program is equivalent to the input program, or it returns a set of counterexample inputs. So these counterexample inputs are the key for making our search efficient. The search algorithm takes into account all of the counterexample inputs seen so far and tries to construct a solution that applies just for those counterexample inputs. And in doing so, um, we create this cycle, right? We create a proposed program, then the equivalence checker gives us some counterexamples. We pass those back to the search process, which then proposes a new program. Um, this algorithm is called counterexample guided inductive synthesis, or CGIS, and there is a pretty rich history of applying this to a bunch of different domains. And for Dexter, we applied it to image processing. So you might be thinking, what is the difference between program synthesis and machine learning in kind of our convolutional neural network sense, where we have stochastic gradient descent doing the search? Um, the major difference is that synthesis is guided by counterexamples. There's no gradient, so you kind of don't have a direction where you are guaranteed to make progress. Um, In addition, the criteria generally is absolute correctness for program synthesis. That is, for every possible input, the outputs need to be exactly the same, rather than minimizing some quantity that is common in stochastic gradient descent. Um, And lastly, synthesis searches over a syntax generated by a grammar, whereas SGD is adjusting weights within a fixed neural network. So the sum total of all of this is that the program synthesis is a fairly heavyweight tool when you're trying to ensure that the semantics are exactly the same. And that makes it difficult to really apply in cases where you're trying to find approximate um, equivalence. So, what does program synthesis enable in Dexter? We applied it to a corpus of 353 performance critical functions from Photoshop. These were functions, some of which had been hand optimized to use SSE intrinsics and AVX intrinsics. Others were just complicated pieces of code that were hundreds of lines, and with little to no commentary dictating or showing what those pieces of code did. Of those, Dexter was able to translate 264 or 74.7% successfully automatically. Um, the total compile time here was 200 hours on 60 cores. Uh, as you can see, this is a fairly heavyweight uh, piece of machinery to run. However, even given that, I would say that in terms of the programmer effort to translate 353 performance critical image processing functions, um, I would call it a huge win. Saving 200 hours is pretty great. So, what happened for the ones that we were not able to translate? So, 57% of those were just due to our prototype not supporting all C++ features. You know, some of these things used structs and other kinds of C++ isms that our fairly simple C++ parser couldn't really deal with. And 43% timed out because the synthesis problem was too hard. And I'm going to talk a bit more about that in a couple slides, but that's kind of fundamentally the difficulty of applying program synthesis, is that really most of the work in building Dexter was trying to figure out how do we scale program synthesis up to being able to handle real world image processing code. So what we did with these translated functions was then to apply a really simple and fairly generic schedule to that. We just decided, let's parallelize the outermost loop. So let's parallelize across chunks of rows, and let's vectorize the innermost loop for all of these image processing algorithms. Um, and To do so, we utilized Halide and we targeted an AVX2 uh, capable machine. And if you look at this chart, what you see is the speed up relative to the input code. And that input code had mostly been hand optimized for SSE2, or was relying on automatic general compiler optimizations. Something like 70% of the translated functions were faster than the original ones. There were some that were slower for various reasons. Some of these were glorified versions of memcopy. So really, we should, just be using memcopy in some of those cases. Others that were slower just had complex uh, uh, indexing arithmetic that we could probably do a better job of translating. But the geometric mean of speed up here is 3.36. And again, essentially, by automatically applying this tool, we not only get the output declarative version of the algorithm, but we also can apply these schedules and automatically get faster performance. So a subset of these are in fact shipping in Photoshop today. So this is a rare example of a programming language tool that actually um, impacts a product by speeding things up automatically and then translating that to uh, actual user experience in the real world. So program synthesis has a bunch of limitations and open problems. So like I said before, depending on the semantics, proving equivalence can be intractably hard. In fact, it in some cases boils down to the halting problem. So we know that even theoretically, we won't be able to synthesize everything. Um, Even for the subset of semantics that we supported in Dexter, it is far harder than NP hard. This is like in P space star, which is a much more difficult equivalence class of difficulty. Um, and the other aspect that's really, really difficult, I think, for the HPG audience to understand, for us to keep in mind, is that floating point operations are really difficult to synthesize. So that makes it really hard for a lot of the problems that in graphics that we're really interested in to apply this technology. We're continuing to work on trying to make floating point operations easier to synthesize, but basically, you essentially have a field that's 16 or 32 bits wide, and the operations really are complicated to reason about, particularly things like divisions. Um, The other aspect is that in high performance graphics, a lot of our problems are amenable to approximation. So approximate synthesis is an area where there's a lot of research happening. It's still fairly new, and the techniques are fairly limited. But the other thing that people try to do is just use ML-based techniques because when approximation is appropriate, you can often get better approximations using machine learning than trying to uh, synthesize a approximate algorithm. And so perhaps one day there will be a way to unify some of these techniques. I'm going to point out a paper that will be in SIGGRAPH 2022 later in this talk that might be of interest to people who want to see kind of where that area is going. Um, I think, Bernd, that's a great question. So we did not attempt to convert Halide back to C++. Basically, Halide is embedded in C++, so what you are getting is C++ code that uses libhalide as a compiler. But what one thing that compiler does support is to actually output code back to C++. So Halide itself can actually generate C++ code. We did not actually try to utilize that capability, but I think that's a good question. My suspicion is that it would differ drastically from the hand-optimized versions, simply because those hand-optimized versions mostly are written using a mix of SSE intrinsics and a bunch of preprocessor directives. That's what the original code looks like. The output code would instead rely more on structures that, or data types, I should say, that are supported by LLVM and Clang, as well as GCC, to better express vector operations in C++. So the code itself looks quite different. I think fundamentally, some of the optimizations would be the same, perhaps with different tile sizes and with different vectorization lengths. So the last tool I'm going to talk about here is kind of in, also the vein of applying a lot of compute at compile time, and that's sparsity-specific specialization. And that really applies for sparse computations. So I know that coming from the simulation world, before I was at Adobe, I had a career where I was working for the Department of Energy on all kinds of simulations in high performance computing. We like to think of the world as sparse. The connectivity of things is just not dense. So in order to represent that and to compute on the world, we often use sparse matrices. And here's an example of a sparse matrix that I believe represents part of a simulation that happens on a surface of a wing. The behavior of the underlying computation depends really on the structure of this matrix. So that makes sense because the sparse matrix is really representing the connectivity of the world, which really doesn't have everything, directly connected to everything else. So the non-zero structure, or the connectivity of the thing you're representing, really dictates how simulation occurs. A lot of codes leverage this structure to avoid unnecessary complexity in the code and unnecessary computation. For example, you can represent convolutions as sparse matrices, but often people just do it directly because that way, you can avoid a lot of the computation. In many cases, the convolution is a image filter, for example, so the weights, and that makes it easy to express as code rather than expressing as uh, sparse matrix operations in which you have to load those weights. So what sparsity-specific specialization really is asking is kind of the dumb question of, what if we compile the code separately for each sparse matrix? The idea here is that we want to expend a lot of effort at compile time to save time during the actual computation. And some initial work in this area we published in SGP in 2020. We took the Eigen API and we basically compile it into vectorized CPU code for a specific sparsity structure. So this isn't quite making it so that we're compiling for a specific sparse matrix, but we are compiling for that specific sparse matrix structure. If we change any of the values, that's okay. But if we change the locations of those values, then we have to recompile the code. And that actually applies to several areas in simulation and other domains where we may be using the same sparse matrix structure repeatedly to perform computations. There will be a follow-on work at SIGGRAPH 2022 where Philip Hurls and some more collaborators apply the same techniques to generate fast GPU code and also scale up the size of matrices we can handle and get even better performance than our 2220 paper. In another vein, SimPiler, which was at supercomputing in 2017, tries to generate solver code for specific matrix structures. So this, is really about direct solves for the most part, although, we do support some iterative solves in this library. But the idea there is that for most direct solves, there is a phase of doing analysis on the matrix structure before actually executing it. What SimPiler does is to actually take that analysis phase and generate code that is specific to that matrix's structure. So let me give a cartoon example of what sparsity-specific specialization looks like. Suppose we have this really small sparse matrix, and we're doing this sparse matrix vector multiply. The red here are non-zeros, and the grays are zeros. If we write this as a dense loop, it just looks like a couple nested loops. We have some index calculation, but there's a bunch of wasted work. We don't need to do the multiply by zeros. So what people often do is to write it, as a sparse computation. You change the data structure. Now in this case, we have uh, uh, an array II, which contains the I locations of each non-zero, and a array JJ, which contains the J locations of every non-zero, and avals contains the value at that non-zero in the sparse matrix. So what sparsity-specific specialization really does is think about semantically what is the computation at each output location. So in this case, we can actually symbolically figure out what is the output computation, and then we generate code that is exactly that symbolic computation. This allows us to store the values densely and to not really worry about the indices and avoid the indirection that you get in the sparse case. Now, of course, the truth is if you actually generated that code, it would be extremely slow because all we've done is move the problem from loading data values to loading code that contains those data values. So that is not necessarily the most efficient way to do it. Instead, what we want to do is find clever ways of grouping that code so that we can transform it into a set of loops that efficiently compute. The way we do this in eggs is to aggregate expression trees with abstract data. So what I mean by that is, for example, we take every case where we have a tree where the output is the addition of two multiplications of values, some coming from the matrix and some coming from the vector, and we aggregate all those into a bunch of loops over similar trees that are then vectorized. What this enables us to do is to actually output code that is much faster than general computation on sparse data. Here I'm showing three different linear algebra expressions that we compare our performance of eggs against writing that code in MKL, which is the fastest sparse library really around. And what we see here is that we can obtain speedups of almost 4x by avoiding redundant computation. I think this is especially clear in cases where you're multiplying sparse matrices because your intermediates may have entries that then end up being zeros. And if we symbolically analyze the output at compile time, we can avoid computing with those zeros for our intermediates. I would say that for the most part, the savings here come from two different places. One is saving in memory bandwidth because we're loading fewer indices, we're avoiding redundant work, and the other is also from more efficient compute. Mostly that is just not computing things that we're not going to store. So with many collaborators, we've published a series of papers. I think that would be of interest to the HPG community. Um, this includes applying the eggs technique to GPUs, which will be presented in SIGGRAPH in just about a month, as well as a series of papers that were at Supercomputing and at SIGGRAPH, where we apply these techniques to create faster sparse matrix solves and faster QP solves. And the results of these are open source and available really easily if you simply search NASOC or Parsai, and the first author, Kazim Cheshmi, who was a PhD student at the University of Toronto. To end with, I'm going to kind of outline a few further directions for this general application of compute power to making programming faster. The first thing that I alluded to earlier is how do we combine really the nice parts of program synthesis, which really does well for domain-specific building blocks, along with stochastic search. And in this vein, Karima Ma, who was an intern at Adobe when she started this work and is a student at MIT, will be presenting a paper at SIGGRAPH in a month or so, which really shows the application of a kind of program synthesis, which is kind of the most basic thing, which is randomly search over programs, combined with stochastic search for optimizing each of those programs for a particular algorithm. In this case, what we did was to look at existing demosaicing algorithms and try to extract what are kind of domain-specific building blocks from the non-machine learning versions of those demosaicing algorithms, and combine those with machine learning building blocks into a large search that searches both over the overall program structure as well as the weights um, for optimizing that for this particular problem. So I think that's going to be a really great talk. You should definitely attend and listen to it. Another spiel that I want to put out here is just that in everything I've talked about so far, it really is a matter of throwing more compute power to the programming and compilation side of things. Um, the scheduling language aspect, though, is really also talking about programmer efficiency. In that vein, I also want to point out another area of really exciting research that I've been lucky to be involved with, which is revisiting program language syntax. Now, mostly PL research has been ignoring syntax for years and years, kind of really treating it as like, well, it doesn't really matter. What's really interesting is the semantics of different languages, because that's how programmers really have to think about the code. Um, I want to argue for a uh, renaissance of syntax because I really do think that we've ignored some of the convenience of syntax. Um, for example, when it comes to markup, Markdown has really simple and intuitive syntax that makes it easy to write Markdown code and have that get translated to HTML and other other outputs for presentation. Anyone who has tried to draft math, for example, I hope would also argue that math syntax is important, and what we've been exploring with this project, iHeart LA, is how can we actually make it easy to communicate math and to communicate math in a way where it's also executable. So our inspiration really was whiteboard math, and we tried to create a language that looks as close as possible to whiteboard math, so that a person looking at a piece of code in iHeart LA will see something that looks like math they're used to seeing written on whiteboards, written in papers, and then we can compile that down to LaTeX code. We can also compile that into executable Python, um, using NumPy and SciPy libraries. We can also compile that down to C++ with eigen. So, uh, and I should also say that one of my collaborators would be very disappointed, Alec, if I didn't also mention that we have MATLAB output for this piece of code for iHeart LA. So that was in SIGGRAPH Asia in 2021. I really encourage you to take a look and kick the tires. We have a demo page online that lets you try to write some code and see what the output looks like. And lastly, I want to give a encouragement to take a look at a paper later on in HPG on Thursday. Andrew will be presenting a paper on better fixed point filtering with averaging trees, which also throws compute at figuring out what the best averaging trees are for various algorithms. It I think is a really cool piece of work with really interesting um, results that everybody will enjoy. I want to, of course, thank the huge amount of collaborators on these projects. In particular, a lot of the halide stuff that I presented in the beginning, really the credit goes to Jonathan Reagan Kelly and Andrew Adams, and the many developers that kind of got that compiler to the point where we could start building a whole bunch of research projects on top of it. And of course, all of the interns and students who do most of the work uh, and uh, are really the hardworking engines for all of research that I'm sure we see in the entire conference. So now I'm ready to take some questions. I will leave some time for that. And thank you for having me once again. Yeah, that's a great question, Bart. The question is around. Sorry, go ahead, Tammy. Do you want to read the
Sorry,
question?
there was a little technical glitch. So
No
thanks
problem.
a lot for the presentation and this very inspiring talk, Shoaib. And we have a couple of questions. We have plenty of time for questions, so let's go one by one. The first one that was asked here is, can Dexter also convert halide back to C++? And if so, much did differ from the unoptimized version? I think this question was answered during your presentation. Yeah. The second one is, do you envision something similar for more heterogeneous workloads like graphics, where there are elements of fixed pipeline like rasterization, ray tracing, or GPU tensor cores?
I think that's a great question. So what I really envision here, and my hope, is that we can start by building the building blocks for the various pieces. Languages that allow us to build better rasterization, ray tracing, and so on, and to find ways to actually integrate those sublanguages. Now, in the case where you have heterogeneous workloads where there is hardware that specifically supports those operations, I think in that case, what we really are trying to do is to support those pieces of hardware through various domain-specific languages. In particular, I think it is a goal for researchers working on Halide to support the tensor cores out of Halide. It is not easy because I'm sure, as you're aware, the data has to be in particular layouts in order to use that hardware. But yeah, I mean, I think that the heterogeneous problem is makes things quite difficult because it's really hard to cross language boundaries. Um, my hope, though, is that we can start by building building blocks that do a good job on the various pieces, and then we can start thinking about how do those get integrated with one another, or whether they even need to get integrated with one another. It may be the case that you just leave outputs in your GPU register file, and then the code generated by the next part of the pipeline can just take those.
Thanks. Guys, don't hesitate to ask more questions. I see another one. In the case of the paper, I love linear algebra. Is it easy to accommodate newer grammars or representation lexicons, symbols, as many people have different ways of writing the same set of equations?
That's a very good question. I think at the moment, we've really been concentrating on convention and having an opinionated convention. And what that really means is that right now, there is a single grammar that does allow people to express things in a few different ways, but for the most part, we've kind of settled on like, this is the way to, write multiplication. This is the way to do, write sine and cosine, for example. What you're pointing at is a really interesting area, I think, of future research, which is kind of a how can we have more of a plugin syntax in the front end for iHeartLA? There is precedent for things like that. There are programming languages like Racket that essentially allow you to completely change the syntax. The default syntax in Racket is something that looks like Scheme or Lisp, lots of parentheses. But there are also plugin syntaxes that look more like Python, others that look like documentation markup. So right now, I would say for iHeartLA, we have not yet thought about the problem of changing front end syntax easily, but I think that's an interesting future area that we should think about, because I think if there's one thing that's as contentious as Vim or Emacs editor wars, it is math syntax wars.
Thanks. The next question in line is, did the translation of unoptimized code to Halide bring up bugs that hadn't been discovered before?
That's a great question. In the process of building Dexter and doing the automatic translation, as far as I remember, I don't think we found any true bugs. We had some things that were I would call implicit semantics. So these were things where, for example, the input and output have to be the same array, but that wasn't expressed in the original code. In our hand optimization, in our hand porting that we've done outside of applying Dexter, absolutely. There have been cases where we discover bugs that have to do with corner cases where, like, if you have the extrema value, you won't get the answer you expected in C++. And as you can imagine, this is a difficult thing to try to figure out, because if the bug has existed for so long, is it a bug or is it a feature? at that point.
Thanks. While maybe some other people may ask questions, we do have time. I do have a few ones. The first one for me is coming back on one of your statements that graphics problems are often amenable to approximation. That is absolutely true. And the thing is, when we write a graphics algorithm, very often the end algorithm is itself an approximation of the original intent. And so I was wondering whether there was a possibility to provide suggestions of optimization while writing the algorithm, because two different algorithms might lead to very different set of samples, for instance, on some domain, but those two set of samples might be equally good at integrating a given function on this domain. So while designing the algorithm, having optimization cues sounds intriguing. And I was wondering if you explored this direction in the past.
Yeah, so I think some work related to things that we have been working on really are applicable in this direction. So one area that one of our former interns at Adobe, Pavel Pencheka, who's at the University of Utah, has been exploring is how to actually suggest to programmers more accurate ways of expressing a computation. So, floating point itself is an approximation in a lot of ways, right? So what his work really is if you have floating point expressions that you're writing during your code, how can you actually rewrite those expressions so that they have less error? So that's one area where, throwing a lot of compute at something is one way to do that, and the underlying algorithm that they're using there, considers all possible rewrites. In terms of the optimization opportunities, um, I believe some of the auto scheduling work that we've been looking at also is in that vein, where it's a starting point for doing optimization. Um, It does not, at this point, really take into account approximation. So I think approximation there is an open area that none of the stuff that we've looked at really has considered heavily.
Thanks. We have a question on the board by Nathan, actually. Hi, Nathan. For future languages, how important will it be to add constructs to more deeply communicate with the compiler in a two-way dialogue?
That's a great question, Nathan. I think that it is going to become more and more important to do that for programs in which absolute performance is the end goal. So basically, for many programs, like good enough performance is fine. But when you really, really care about that speed, I think that it does really require conveying rich semantic information to the compiler in order to um, give the compiler enough information to apply particular optimizations or to prove that optimizations the programmer is asking for are valid. Um, and so in that sense, yes, I do think it's going to become more and more important, as code gets more complex, as code really starts dealing with multiple data structures, with various different options in how that data structure can look like. Deeply conveying the semantics to the compiler in order to take advantage of more complex hardware as well is going to be more and more necessary. Um, the nice thing is that for libraries, a lot of times um, you have vendors or other library writers who are able to give you good enough performance in most cases. But for the real high performance algorithms that a lot of us really care about, this is going to be really important.
Thanks. We still have time for one extra question, I think one or two if needed. I do have another question, which is might sound a little bit exotic, but I will ask it still. So over the last 10 years, we saw more and more 3D assets coming as parametric objects instead of static data. And so when you look at those objects, materials, shapes, even lighting environments, they actually come in the form of a graph. which in itself is a program that is run by some execution engine that produce some low-level code that some rendering engine can actually interpret. And so assets become logic, assets become program in this scheme. And I was wondering if you looked into asset optimization, that kind of asset optimization, through methods such as the ones that you have been showing today.
That's a great question, Tammy. This is an area that I'm very interested in, and some of our explorations there are, I would say, nascent. But the key idea is exactly how you're describing it. Basically, right now, the way these things are kind of created is that you have this graph that's interpreted. And one thing that we've been really trying to explore is, can we actually consider the thing that generates code for that particular graph as a compiler? So instead of doing just stringing together local operations, which is mostly what today's engines do, can we actually try to treat it as a compiler and do a global optimization, or do an optimization that's guided by programmers? I think that's not as exotic as you think. It's something that we really would like to do, but I think it's very early in those explorations. And in general, I think there's a lot of areas where we have things that are currently run through what I would call interpreters today, which really just deal with like one node of a graph at a time, um, that we would like to turn into compilers, where now we can try to consider the entire node graph as a program, and we can do things like eliminate redundant computations and do optimizations across the entire graph. You see a lot of this work in the machine learning world already. I think a lot of the recent performance improvements we're getting is just due to things like collapsing together some of those memory bandwidth bound nodes so that you don't read and write from memory back and forth. You just do the computation in memory, for example. And so applying that to those kinds of asset graphs is going to be a really interesting area of research.
Thanks a lot, Shoaib. The time is almost off. Thanks for all these answers and the talk and the keynote. That was really inspiring. This will conclude the keynote for today. Everyone, we can probably thank Shoaib again.
Thank you for having me.
Thank you. Well, I hope you will all enjoy the social rooms that you can join during the break. We are having a short break now, and we reconvene in